car rear roof spoilers are very useful tools. They're these little flicks at the back of hatchbacks that we can see here in this idealized figure. And something that they can do is reduce the lift of a car and even increases downforce, which often leads to better handling. But they can also be used to reduce a car's drag and even make it more stable in the sideways direction. And while they can do all these things, there is no one universal design that is used. As shown here, in the right portion, we see the outline of the spoiler, so these little black lines. And the rear window is this major slant going down, and then the roof is to the left. And we can see that this is all different angles for this rear spoiler. So how do all these different angles affect the flow in this region, and namely the lift and drag? But also, does pitching this spoiler at different angles affect the forces on the regions located quite far away, for example, the front of the car? And this isn't as daft a question as it might seem, because I mean, this spoiler is literally at one end of the car compared to the front, so its effects should probably be isolated, but perhaps not, because this spoiler is affecting one of the most important parts of the car, the base and the base wake, so the rear of the car. And because it will affect this very important region, there could be some major upstream effects. And there are really only three ways to avoid upstream effects. The first is to make the device good enough to not have upstream effects, or at least negative ones. Then a second is to somehow isolate its effects from the upstream portions of the car. Then the third way of making sure that you don't have any upstream effects, and my favorite, is to drive fast enough that downstream effects can't propagate upstream. So around Mach 0.8 or so should do. So today we're looking at how different spoiler angles affect not only the overall drag forces on the car and like the lift as well, but also the flow around these regions and the entire car. So to do that, we are looking at this paper. If I scroll up here, it's called The Influence of Rear Roof Spoiler on the Aerodynamic Performance of Hatchback Vehicles. It is open access, so you can find the link below, and the DOI is in the top right for those interested. Now, let's see what they did and what they found. So as I mentioned in figure 1, this is the general setup, and this is the geometry they tested too. And it's obviously not a car, it's actually an armored body. And the armored body actually is a very standard geometry used to test and investigate the effects of various flow control devices and geometric changes to cars. So the reason is because it produces most of the major flow features you get on a car. And in this case, things get even better because these researchers are looking at a hatchback, and hatchbacks are even more similar to armored bodies than other types of cars like sedans and even fastbacks. For example, if you look at the bottom of the armored body here, you'll see that there is no diffuser. We have this green face at the bottom of it. The undersurface is just completely flat. So for cars like sedans and fastbacks, that's not great because they have diffusers almost always. Hatchbacks, though, they don't have diffusers usually. Usually the back of the car ends very soon after the rear wheels. So in that way, an armored body is actually more similar to a hatchback. Another important feature of an armored body is the rear slant, or the rear window, so this grey part here. Hatchbacks have this exact same geometry, and the amount the rear window slants down varies between models. And then they also have this spoiler just pretty much above the rear roof, and it's almost like mandatory for any hatchbacks these days. In fact, if you go out onto the street now and look at all the new hatchbacks driving by, you'll struggle to find one without this spoiler. So the armored body, while it doesn't look like a car, has many similarities with cars and especially hatchbacks. And before we go any further, let's talk about why cars have these spoilers. I mean, why have them in the first place, let alone optimize them? Why not have nothing there and then the rear window just coming straight down? Well, there are a few major aerodynamic reasons why you wouldn't want a spoiler, why you would want a spoiler between the roof and the rear window. The most obvious one is that you can guide the flow however you like. So if you want more downforce, you can flick the spoiler up so that as the air travels over it, it gets pushed up, and then that creates more downforce into the road. That means then you can lay down more power because you have more traction, which means that you can accelerate faster. Another major advantage of this spoiler is that if you didn't have it, the flow will likely separate as it reaches the rear window. Even on the gentler slopes of the rear windows of hatchbacks, they're still way too steep for the flow to stay attached, so it separates. So you might be thinking, well, big deal, you get separation there, and if you put this spoiler thing on, you'll still get separation, so what's the big difference? While it's true that both produce major regions of separation, with this spoiler, you often get smaller wakes because they become more stable. So the wake over the rear window is usually just this pretty stable recirculation region which occupies mostly the same volume. On the other hand, the wake from a spoilerless rear will usually be bigger, and it's usually a lot more unsteady. So that smaller wake often comes with a reduced drag too. Now another major benefit of this spoiler is that because the wake is much steadier, it doesn't flap around as much, the forces on the car become more stable, so it makes it easier to control. So all these are some major aerodynamic benefits, but again, the exact geometry of the spoiler has large effects on these benefits too. So we'll see how changing the angle here really affects the flow and then the forces on the car. So the authors give some details about this spoiler. They say at the top of this paragraph that they have it at 66.6 millimeters in length, and then they tested it from minus 15 degrees to 0 to 5 to 10 and then finally 15 degrees. And in this outline in the right here, you can see that minus 15 degrees is the configuration where the spoiler is actually very low. It's sloped down, it's the lowest one here. And that's quite common to see these days, this particular setup. Then they looked at other configs ranging from level to poking up at 15 degrees. So in this study, they used CFD to determine what the effects of these different geometries were. They used RANs, which isn't ideal because the flow around the car will be unsteady. And in fact, I actually think that it's worse for this armored body without the spoiler because the flow will be even more unsteady. So RANs doesn't capture that unsteadiness. So whatever the accuracy will be for this regular armored body, I think it will be better when you put the spoiler on because the flow will become steadier, which fits the RANs approach better. That's my opinion. And because they used RANs, the researchers also took a very common approach, which is they simulated only half a car. So in figure 2 here, if I scroll down, here we go. So in figure 2, we see the domain and their armored body is in this blue, purple, and orange part. They sliced through the center line of it, and then they applied a symmetry boundary condition on that face to then replicate the other half of the car. So the reason why this is such a common approach to take when you're doing RANs at least is that the flow in RANs is supposed to be steady. So because it is steady, the car is symmetrical and geometrically, that means that you only have to simulate half the car and then you can just mirror it about that center line and get the entire car. That's the thinking at least. Now in reality, the strange thing is that while RANs should give a steady solution in theory, in practice it usually doesn't for bluff bodies, like an armored body or a car. There are actually fluctuations, and that is because of the imbalances in the flow, because the flow is unsteady, and those unsteady features are kind of muscled in despite the RANs equations not explicitly being able to do unsteady flows. There's no time aspect for RANs equations, but still we get a pseudo-time effect bleeding through. So while this approach of using RANs with a symmetry more down the middle is okay, if you have the cell suspend, then you should probably start simulating the entire car for a better result. As for the cells, they use an unstructured mesh, which is good because the flow here should have a lot of swell in it, and the unstructured mesh picks that up a lot better. And because they used an unstructured mesh, they had to use 890,000 cells, which isn't very much, but they said that they conducted a mesh independence test, and that gave the results converged. So 890,000 cells was how much they needed to get a converged solution. Now I can't see any details about this test in their paper, and that's not good. I mean, even though it is just a conference paper, if you want to make a greater impact for your paper, even if it is just a conference, you should still add important information like that, which would then increase its validity and then people will trust them more. Anyway, the velocity was 40 meters per second, which gave a Reynolds number of 768,000 based on the model height. Now, I don't know why they used the model height. Usually you use the model's length here, but because they were thinking about the vortex production of the armored body, maybe they decided that the height was more appropriate because that is the driving length scale for this particular flow feature. Anyway, the turbulence density was 0.2%, and I'm not sure why they chose that turbulence density either. They do validate their CFD later on against experimental data, so maybe that was the turbulence density in that data, but they don't say, so I'm not sure. Anyway, that percentage is pretty similar to regular automotive wind tunnels, but much lower than real life, which is more like 5%, 10%. And while having a lower turbulence density than real life might be quite bad for a lot of cases, here this body actually has very sharp trailing edges and even side edges, so there shouldn't be that much of a difference in the results, and the flow is almost certainly fully turbulent here. So you can see here how sharp these edges are. So it should be fairly turbulence density and even Reynolds number independent above maybe around 300,000-400,000. Now, they had a y plus value ranging from 1 to 57. Now, this is an interesting point because their Rand's terminus model that they chose was the K epsilon realizable. So here they say K epsilon realizable. So there are a few details here we should cover regarding the accuracy of this mesh with the chosen terminus model. So for the K epsilon family, you usually don't want a y plus value below around 15. Some estimates go down to about 10. So the reason why you have a y plus value below 15 and definitely 10, which then make CFD worse here, is because simulating the boundary layer wouldn't be as accurate for the K epsilon model. The equations you use in this model, in this family in general, just aren't designed to handle the flow physics that close to the wall. These researchers had y plus values down to 1. So that usually would be bad. You would want to make the boundary layer mesh coarser in the height direction to get that value above 15. That is what you typically do. Researchers here, they said that they use something called the enhanced wall treatment option in ANSYS Fluent. Now I looked into this option on ANSYS's website, and apparently this option now allows you to use lower y plus values near the wall for the K epsilon family. I'm not sure how much more accurate it is because I couldn't find any studies on it on their website. Maybe I just didn't look hard enough. But anyway, they said that it makes the simulation more accurate with this enhanced wall treatment. Now, just as a side note, I'm not sure why you'd want to use that anyway, because it seems like that's an additional equation or an addition to the equations that you use already, which would then make the solver slower. One of the major benefits of the K epsilon model is that you can have a coarser boundary layer mesh, which means you have fewer cells, and then you don't get that benefit now because you're using more cells. So why not just go to like an SST or KME SST model, which is more accurate generally anyway, with the same number of cells. Anyway, this blockage ratio in the domain was 1.5%, which is really low. That's really good. With that kind of number in a wind tunnel, you wouldn't need any correction factors. But I'm not sure what the blockage ratio was for the study that they got their experiments from, their data from there. Let's move on now to figure 3, because we see their CFD results, and it's a cut plane down the center line, showing the normalized velocity to the free stream velocity. So it's just whatever velocity it is at that point, divided by the free stream velocity. So it goes from minus 0.3 to 1. So the wake seems very armored body-like. In table 1, we see the drag coefficients from their CFD compared to the experiments. Overall, there was a 2.7% difference between the two, which is really good. But one interesting thing is that they give a breakdown of the different regions and the drag associated with them. So that's really cool. Around the spoiler, so the slant and the base, they get very similar results, like 2% difference. However, the front is very different. They get twice as much drag from here than in the experiments. Now, I'm not exactly sure how they calculate these numbers or how the experimental data was taken in order to make this breakdown of these numbers, but they get a difference here of like, what's that, 24 counts. Another interesting note is that the viscous drag coefficient is very similar, only 6 counts off. That could be because the boundary layers are very similar with that enhanced wall treatment, or maybe just the errors happen to cancel out, I don't know. Anyway, the drag coefficient looks pretty good, but I would be hesitant to really say that the accuracy is 2.7% because of the number of simplifications to the CFD, including the RANs, then the symmetry, and then the terminus model used. So perhaps just looking at the trends from here and the exact numbers is just a general guideline. That would be a better idea to go along with. And just quickly, if you want to learn OpenFOAM, which is a really powerful and free CFD software, then check out our courses here. Let's now get into the results. So in figure 4, we see the effects of the spoiler angle on the lift coefficient. As expected, increasing the angle so that it's poking up more and more into the flow reduces the lift coefficient and eventually produces downforce. One thing that is a little surprising to me, though, is that this line is pretty much linear. So changing the angle between minus 15 and 15 degrees yields a very linear response. Another interesting thing to me is that downforce is produced before you even get to 0 degrees. So completely flat, you're still already getting downforce. So if you want to some downforce for this geometry, you can get it even with the spoiler angled down maybe 2 or 3 degrees. Now, this is also taking into account the armored body and its vertical force, and that effect on the lift coefficient, but still here for this geometry, a slightly angled down spoiler is still good enough to get downforce. So in figure 5, we see the pressure coefficient in the center line, the center plane, slicing straight through the armored body, and with different spoiler angles. So there are a few things to note. The first is how low the pressure is. So blue here in the region behind the geometry. In the bottom right, you can see that there is this major blue region high up. That tells us that the wake is very large here because there's so much blue. This is the wake. So this spoiler angle should be producing a lot of drag. On the other hand, in the bottom left figure, the blue is much lighter behind the armored body and even a little green higher up. So its wake is much smaller and we should be getting lower drag here too. Another important point is on the top of the car, just in front of the spoiler, we see that the spoiler angle really changes the pressure coefficient here. And actually in the bottom left figure, which is with the spoiler at minus 15 degrees, so it's angled down very much, the pressure is very low. So it's very blue just ahead of the spoiler, which is where we get much of the lift coming from that we saw in figure 4. So this low pressure is really pulling the car up and creating a lot of lift, particularly over the wheels, the rear wheels, which would probably be bad for handling and acceleration for most cars. On the other hand, in the bottom right, which is the spoiler at 15 degrees now, so it's poking up at 15, we now get even red in this region ahead of the spoiler. So very high pressure, which pushes the car down into the road and creates more downforce. That means that you can probably accelerate a bit quicker and go around corners a bit quicker, usually. The arrows now also give a good indication of what the flow is doing. So for example, in the bottom left figure, the arrows are angled down more over the spoiler and the rear window. So the spoiler is kind of guiding the flow down in this direction. Likewise, in the bottom right, the arrows are slightly pointing upwards as the spoiler kicks them up and creates downforce. Now for the top two figures, we see that on the left, the regular armored body without any spoiler, and then on the top is with the spoiler, but it's now flat, so it's 0 degrees. So in effect, it's just an extension of the roofline. We can see that over the rear window, so the slant, the pressure is higher when you have the rear spoiler. That is something that manufacturers have really taken advantage of and embraced a lot by adding it to pretty much every hatchback these days. They can really isolate this region, increase the pressure here, and then reduce the drag of the car because you have higher pressure on this face. So one thing that is surprising as well is that the arrows are pretty much the same between no spoiler, so the top left, and then with the spoiler flat, so the top right. Now, I guess this is an average simulation, so it's RANs, so the circulation and its unsteadiness isn't given here, but still the averages are pretty much the same. So the actual direction of the flow isn't impacted much by just extending that roof line. So now in figure 6, we see the pressure coefficient on the surface of the armored body center line. Note that this isn't like towards one side of the body, it's just the center of this armored body, which is informative, but it doesn't take into account the 3D effects you get from the flow on the sides of the car, affecting the flow on the top and vice versa. So this is just a limited view of what is going on at this particular point and not the entire car. Now they have the bottom and top pressure coefficients plotted in this graph, and the solid line is without the spoiler, then the dashed lines are with the spoiler at different degrees. Note that there is almost no change along this line until you get about 50%, so X on L is about 0.5 here. Then you start to get some differences, but only really for the spoilers that are either plus 15 degrees or minus 15 degrees, and particularly the plus 15 degrees one. The reason why we get such a big upstream effect from that one is that it pushes back on the flow, and that increases the pressure, and that migrates upstream as well. The other two spoiler angles plotted here don't create that air damming effect. They actually let the flow go either unhindered, or in the case of the 15 degrees angled down, it actually encourages the flow to accelerate along, and that drops the pressure upstream a little bit too. So around the spoiler is where we get most of these changes occurring though. In this plane, they effectively are localized to just around the spoiler, and that kind of makes sense. Let's now move to figure 8, where we get to see the lift and drag coefficients. So we see it's plotted like a drag polar plot, which is the quintessential aeronautical graph, but it's a little hard to read for cars. Anyway, interpreting this effectively as expected, as you pitch the spoiler up more and more, the drag coefficient increases. The increase isn't linear, the slope actually increases as well. So that means that if you pitch up the spoiler more and more, that produces more and more drag in like an upwards fashion. Those are the overall trends. Now in figure 9, we see a breakdown of the lift coefficients of the different regions of the car, and how they change between the different angles of the spoiler. The blue lines are how much the lift coefficient changes between the spoiler at 5 degrees and 0 degrees, while the gray lines are changes between 15 degrees and 5 degrees. And remember that the more the spoiler is pitched up, the more downforce it produces, so the less lift. In this figure, the spoiler itself is where the major changes occur, with over 100% more downforce produced right here when increasing from 5 degrees to 15 degrees. So 104.8% increase in downforce or reduction in lift. The other regions producing more downforce is the roof. So there's about 10 to 20% increase here. And that's to be expected because in figure 5, if we scroll back up there, we saw the pressure coefficients. And with the spoiler angled up more, so this bottom right figure here, we got higher pressure ahead of it. So that's over the roof, and that's where downforce is going to come as well. So that makes a lot of sense. Then in figure 9, again, we get a somewhat unexpected result here. So every other region shown here is either unaffected by the spoiler angle, or it apparently produces more lift with a higher spoiler angle. So the base, which is the back of the car and underneath the slant, and then the slant too, both produce more lift as the spoiler increases in angle. And actually, while that kind of seems the case, I should probably say that the base numbers, so the far left numbers here, 37% and 25%, they're probably within the error because the base face of the armored body is vertical. So it can't produce lift or downforce through air pressure. So all these numbers seem very high, they're actually probably nothing. And that actually the slant is the only one that is producing this downforce compared to the base, because the slant is now in a direction where the normal vector off of the slant is somewhat in the lift direction. So it can contribute to the lift direction. The base can't do that, it's vertical. The sides are also likely in error as well because they're vertical too. So from this plot, we can see that really the changes in the lift are located around the spoiler, rear window, and the roof. And in figure 6, we saw changes over the roof pretty far upstream, so 50% upstream. So that's pretty interesting. So that indicates that the front of the car isn't affected with these effects really stopping at about halfway upstream of the roof. And with that, we come to the end of this podcast. One thing that was really surprising to me was how linear the change in lift coefficient was with the spoiler angle. The drag coefficient was much less linear. I wasn't expecting that with the lift coefficient. So anyway, if you wanted to learn OpenFlow, then check out our courses in the link below. And if you like this podcast, hit the me liking and subscribe buttons, and we'll see you on. Peace amigos.